right, we're going to start by looking at some subspaces that are related to a matrix. Let's say we have this matrix 1, 3, 5, 2, 4, 6. There are some spaces that go with this matrix depending on how we define them. So for instance, there are numbers here, vectors, that will cause this product to become 0. That is going to be one of the subspaces we're going to study. So if this is 0, 0, 0, then we will have a space of all those vectors. And that space is going to be called the null space, N-U-L-L space. Let's assume this matrix is A. So the null space of A is going to be the set of all those vectors, so that when we multiply those, this one on the right, this one on the left, we end up with zeros. So that's one important space, the null space of A, that we're going to get into. There's also the space generated by the rows. I'm going to label that as the range of A. So then there is the, so there is the space generated by the rows. I'm not going to give it a name actually right now. So if you look at those two, all the linear combinations of those two are going to create a subspace, a proper subspace of R3. And then we also have the space generated by all the columns. So there is the space or subspace, in both cases, we're going to call them space generated by the columns of A. So these are the rows of A and the columns of A. So the columns are two-dimensional. So this subspace is in R squared. The rows are three-dimensional. So that subspace is in R cubed. The null space is also in R cubed because we have 3 dimensions here. Okay, we're going to focus on the null space, but be aware we're going to also be talking about the space generated by all the rows and the space generated by all the columns. There's a few things we have to clarify at this point. So again, sorry if I am repetitive, but it's better to be redundant than not saying things enough times. So we have the space of all the vectors that when we multiply in those two, we end up with 0. There is independently the space of all generated by all the rows. There's only 2 rows in this case. Since those rows are 3-dimensional, the space of generated by those 2 rows lives in R cubed. Then there is the space of all the generated by all the columns. That space, because the columns are 2-dimensional, are going to be in R squared. This is a 2 by 3 matrix. 2 by 3 matrix. Okay. There's a few other things we need to clarify. We may be getting into more than 3 variables. And instead of using X, Y, Z, and oftentimes we would use W, but then after that, we kind of ran out of letters. We start going backwards. So instead, we're going to use X1, X2, X3, X4. And that way we don't run out of letters because we're just using numbers to indexes to replace the letters. We're still using the same X, indicating we have the variable X1, X2, X3, X4. You know, and you can have as many as you want. You can have X10 And of course, those are sub-indexes, so they are on the lower right corner of the variable. So first of all, um, I'm still going to occasionally use x, y, z, especially when we have 1, 2, or 3 variables. But mind that many textbooks and myself, I will start using occasionally x1, x2, x3, x4 instead. Please don't get confused. It is the same thing. Yeah, do not mind that. Okay, we're gonna get into the concept of a free variable. So a free variable will be the one that, as the name implies, can be anything it wants to be, as opposed to a variable that relies on the free variable. So we have dependent and independent variables. Oh, let's talk about solutions, yeah, to things, to problems or equations mainly. Solutions, or kinds of solutions. Kinds of solutions. We're going to start labeling certain kinds of solutions in a particular way. Let's say you have x plus y equals 10. So one solution to this equation will be, say, 3, 7. 3, 7 is one solution. 3 for x, 7 for y. It turns out in this case that 7, 3 also works, but that was because this equation is very symmetric. But I'm just going to leave it alone for simplicity. And you have many solutions, such as negative 2, comma 12. That's another solution. So each one of those are labeled as particular solutions. If we if one of the variables is 1, then we're going to label the solution as a special solution. So 1, 9 is special because of this 1. And we cannot have more than 1. Okay, so this is special. And also 1, once you put the 1 in one place, that forces the other variables to be dependent on that 1. So in this case, there is one variable that is free, whether you choose the variable to be free to be x or the variable to be free to be y. Once you pick one, the other one is determined by that one variable. So if x is 1, that forces y to be 9. And if y is 1, that forces x to be so 9. So in this case, we have to think which one we wanted to be free. But in this case, since we did not have one specifically variable to be free, they could either one could be free. But there's only one free variable. There's not two free variables. This is a little misleading because we may be thinking, oh, so there are two free variables. No, no, no. It is only one, whether we choose it to be x or y, there's only one free variable because the other ones, well, the other one in this case happens to be determined once we pick the free variable. Okay, so this kind of solutions are called special. Now, every special solution is a particular solution. So particular solution is just any solution as opposed to special. And then we have also the general solution. Oh, I guess I was putting the names over here. So what is a general solution? So if we pick x to be free, then the other variable has to be 10 minus x. There. This is not a fraction. I was just putting an underline to emphasize that this is the free variable and this one depends on that. Let me write it the other way. So x is free, and then the other variable, 10 minus x, is dependent on this free variable. But if you want y to be free, then the first variable has to be 10 minus y. There we go. So this is what I would call general. So that means all solutions. in this case. Yeah. All right. So we have particular solution, special solution, general solution. But let's go farther on this. Let's say we have um, an equation. Let's label that as example. This is our example 1, even though we're going to come back to it. This is our example 2. I don't think I'm going to come back to example 2. Example 3, x plus y plus z is equal to 10. Okay, so a particular solution. There are many particular solutions, but let's say one is -1, and then let's say -2, and then, okay, so if I pick those two arbitrarily, -1, -2, that forces z to be 13, because otherwise we cannot make the 10. So two of them, I mean, let's think about this. Can you pick x at random and salvage those two to end up with a 10? The answer is yes, just pick whatever. Can we pick 2 at random and still get a 10 regardless of whatever those two are? Can this one make up for whatever those two are to end up with a 10? And the answer is yes. You, even if you have a -1 million and a -2 million, all you have to do is turn z to be 3,000,010, and that will cause this to be a 10, this addition to be a 10. So it doesn't matter what those two are. This we can always save us and get 10, the z.
Are you there? Are you there?
Hang on a moment.
Are you there? Are you there?
Sorry about that. There was just somebody trying to get a hold of me. So there are two free variables. Those two can be anything they want, and z is determined. And this is a particular solution. A special solution, by the way, any one of those any two of those three could be free. I'm right now picking x and y, but oftentimes we pick the last ones to be the free ones, not the first two. So just be aware of that. But then we have special solutions. So a special solution, okay, back here in example 2, when we spoke about special solution, we have a 1. And you may think, oh, so we just need 1, 1. No, we want the free variables to be 1, 0, 1, 0. And then the dependent solution, the one that is not free, to be whatever it has to be in order for the equation to work. So in this case, we need it to be 9. All right, so this is one of the special solutions, and there are two special solutions, 1, 0, 9, and the other one will be 0, 1, 9, assuming that x and y are the free variables. Had the free variables been y and z, we would have 9, 1, 0 and 9, 0, 1 instead. So free variable is relative. You have to pick who the free variables are. And then once you establish the free variables, assign 1 to one of the free variables and zeros to the other variables. And that will be a special solution. Now, a general solution can be written in many different ways because we actually end up with parametric. So all the solutions, I'm going to label this as all solutions. There are many ways to write all solutions, but x and y can be free, and then z would have to be 10 minus x minus y. So those are all the solutions, the general solution. But one thing we want to be focused on are those two. Yeah, those two solutions. They're going to be quite important for us, those two solutions, the special solutions. And just to be sure, let's do an example 4. Yeah, let's say x plus y plus z plus w. Oh, we have a lot of variables. Let's start using x1 plus x2 plus x3 plus x4 equals 10. Same kind of problem. Okay, and there are many particular solutions, but I want to focus on the general solutions, rather special solutions, special solutions. Now, when we speak about special solutions, we have to determine which ones are the free. And in this case, three of them are free. And it doesn't matter which three, but we pick which ones because the other one is going to make up for the other three so that we end up with 10. So that is not a free variable. So let's, in this case, let's assume the last three are free. Assume or pretend or set last three variables to be the free ones. So free is a little bit relative. Okay, so in this case, what are the spatial solutions? Okay, so we have 1, 0, 0. So since we are assuming that the last three are free, 1, 0, 0, and then we have to figure out what causes this to work, and that would be 9. So that's one of the spatial solutions. There's going to be three spatial solutions, as many. So there's going to be as many spatial solutions as free variables. Yeah. So another one would be 9, 0, 1, 0, 9, 0, 0, 1. So what is important about a special solution is that we have a 1 in one of the free variables, zeros on the other free variables. And there it is. So those are the special solutions. Okay. So what have we spoken about this far? The spaces generated by a matrix, the different kinds of spaces generated by a matrix. What else? And and special solutions. Now, one of the things we want to be able to do is describe. We want to describe a sub vector space. Okay, so we want to describe a subspace of a vector space. Yeah, and it turns out that one of the best ways to do that is by naming the generators of that space, subspace. So at this moment, the way we're going to describe it is by, and I actually, that is pretty much just about the only way to describe it now that I think about it. So we want to describe a subspace of a vector space, and we do that by generators of that vector space. So we're going to focus on the generators of the subspace. Yeah. Yeah. So let's say I want to generate in a three-dimensional space. I want to generate the plane down here. So one way to go about it is to name this vector, and that's it. But somebody could say, well, can we name also this vector? So the space, the two-dimensional space, which is the floor, can be generated by, so we're going to talk about the span of 1, 0, 0, comma, 0, 1, 0. That is sufficient. If we put one more, such as 1, 1, 0, one of them is redundant, not necessarily this one. You can get rid of this one because you can generate this one by doing this one minus that one. So the point here, though, is that this set, so this one set is redundant. There's one too many. Why? Because if you really want 110, you can just add those two and get this one. If you want this one, you can do this one minus that one, and that gives you this one. If you want the first one, you can do the last one minus the second one, and that gives you this one. So all you need is two to generate all the XY plane. We don't need all three. So whenever we're describing a subspace such as the XY plane inside of our cube, we want to have as few as possible. So redundancy has to be gone. We don't want redundancy. Is redundant. Yeah, we want to get rid of all redundancies. We want to be as specific as possible. Now notice that this 100 is simpler than 110. That one is simpler than that. Because it has more zeros. The more zeros we have, the simpler, because then essentially we only have one element. Same thing here. So that's why we prefer those two over that one, if we can help it. Sometimes we cannot help it. So if we were looking at a plane that was oblique, we might have to have a third. In fact, we will have some kind of a third variable. And then sometimes we cannot get rid of that variable, or that constant, rather. But we will still only need two if we have a plane, a two-dimensional plane inside of three-dimensional space. Going through the origin, we only need two vectors, not three. Yeah. So the way to describe a space or a subspace will be by showing the generators of that space. Now the generator is the smallest, in our case, we want to go with the smallest and simplest number of vectors that span the whole, that are necessary to span the whole subspace we want to span. Okay. I think those are the first things we need to address. Let's go back to example 1 and talk about the null space. So we have 1, 3, 5, 2, 4, 6. And we want to find all the x, y, z's, sometimes labeled as x1, x2, x3. Please do not get confused if you see that. So this is a 2. Oh, by the way, I just realized this is, boy, I hate doing this in a video because I don't have somebody to tell me, hey, Mr. Salivar, shouldn't this be a 2 by 1? Because this is a 2 by 3. This is a 3 by 1. So the multiplication makes perfect sense. But this doesn't make sense after the fact. Good thing I'm coming back to this, because the multiplication should be a 2 by 1 matrix, not a 3 by 1 matrix. All right, so we want this to be 0. And generally speaking, we're going to label this as the 0 vector in whichever dimension we need it to be. So this is just going to be the generic 0 vector. Okay. So we have, an x plus 3y plus 5z equals that. And then 2x plus 4y plus 6z equals 0. So in both cases, we get 0. But describing the solution that way is rather awkward. If we only had one equation, x plus 3y plus 5z equals 0, that wouldn't be too much of an issue, although we would like to simplify even that. But that wouldn't be too much of an issue, because then we have the same kind of example as the examples here, like this one, example 3. That would be similar, and that is fairly easy to figure. But we have two equations, one corresponding to this row for x, y, and z, and another one corresponding to, and so we want to really simplify that. And the way we do that is by simplifying by doing row operations. And one of the things we want to do is change this into row reduce echelon form. That will be the simplest way, because of trying to describe the space of all the solutions to this equation. So again, what is our goal? Our goal is to describe the space of all the solutions to this equation. Let's write that down. So we want to describe the space of all solutions to the above equation. Okay. 1, 3, 5, 2, 4, 6, x, y, z equals 0, 0. And then what we can do, so this is still example 1, we can reduce the rows. Now, reducing the rows is equivalent to manipulating the equations. So we end up with two equations that are equivalent to the original equations. So we can subtract twice the first row from the second row. And that will cause, we have a pivot here, and that can help us get rid of this element here. So subtract 2 times row 1 from row 2. A shorthand for that would be row 2 minus 2 times row 1. And we end up with a new matrix, which is 1, 3, 5. So 2 minus 2, 0. 4 minus 6, negative 2. 6 minus 10, negative 4. So what this equation, this new equation is saying is that negative 2y minus 4z is equal to 0. Well, we can divide by negative 2 because we have an equation, and in an equation we're allowed to divide by or multiply by a non-zero number anytime. And that's going to give us an equivalent system of equations. So by equivalent, what we mean is that the solutions are not going to be changed. So we're going to multiply negative 1/2 by row 2, and we're going to end up with 1, 3, 5, 0, 1, 2, x, y, z equals 0, 0. And remember, this means 1x plus 3y's plus 5z's equals 0. 1x plus 2y's is equal to 0. Okay, but then we can simplify this even more because we can take away that 3 from this matrix. So from row 1, we can take away 3 times row 2. And that's not going to mess up this 1 because this is 0. That's why we want to go in descending order, going down the main diagonal of the matrix. Because once we obtain a 0, or we want to go from left to right, clearing up columns. So we have a pivot, and then that will wipe off all the elements other than itself in that column. Now we got another pivot, and that will wipe off all the elements above and below this. All right, so 1 minus 3 zeros, still 1. 3 minus 3 ones, 0. 5 minus 3 twos, negative 1. And then we still have 0, 1, 2, x, y, z equals 0, 0. And this is as simple as we can get. What this is saying is that x minus z is 0, and y rather, y plus 2z equals 0. Let's write that down for a moment. X minus z equals 0. x minus z equals 0, and y plus 2z equals 0. Well, that means that x can be written as z. X and z have to be the same. And y is negative 2z. So that means we have one free variable. This guy can be anything it wants to be, and the other two have to do whatever those two equations say about z. So this equation says x has to be whatever z is, and this guy says y has to be opposite of twice what z is. So z is a free variable. It's only one free variable. Notice that these are the number of pivots. There's two pivot numbers, while this is, yeah. And the number of free variables are the columns that are left over um, after counting all the pivots. So there's two pivots, one column with no pivot. So there's no pivot here. The columns with no pivots are called free columns. Yeah, so this column has no pivots. This one has this pivot, this column. This column has that pivot. This one doesn't have a pivot. So if we don't have a pivot, we call it free column. Yeah. And here's a reasoning why. So the solution set, the general solution set will be, um, so z is free, so z has to go here in the sense that they have to be equal. Negative 2z, and well, z is whatever it wants to be. So this is the general solution. But we want to write solutions, we want to describe solutions, which are subspaces. Not this way. We want to get away from this. We want to show all the solutions in terms of generators. What generates a solution? Okay, let me rewrite this on the next page. So the general solution can be written as z negative 2z z, which is the same thing as, if we factor out the z, 1, negative 2, 1. So the general solution can be generated by this single vector. That is very, very interesting. Yeah. So general solution may be, yeah, generated by 1, negative 2, 1. This is, by the way, a special solution because the free variable, which is the z in this case, and how do we determine that? That's by the, we write this in descending order, and so the variables that are going to be free are invariably going to be the last ones because of the order. This is representing x, y, and z. So if there's only one free variable, that is going to be the last one. So this is in particular a special solution. Yeah, so note we have a special solution. Why? Because the free variable is 1. There's no more free variables. If there were more free variables, then we would have to have 1 and 0, or 0 and 1. Yeah, 1 and 0, and then 0 and 1. And we usually start with 1 and the uppermost free row of the solutions. Yeah. Yeah, so all the solutions are generated by this single vector. Okay, so all solutions to ax equals 0 are generated by 1, -2, 1. By the way, all the solutions to this equation, if we have 0, are called the null space of A. So what we just established is that the null space of A is the span of the set of vectors with a single vector, 1, -2, 1. Now, if you get 2 vectors, that would be redundant, or more than 2 vectors. And this is the one we want because we want a 1 here. You could have 2, -4, 2, for instance. You can multiply this by 2, and that would still work, because 1 is, yeah. So let me establish one thing clearly here. So the span of 1, -2, 1 is equal to the span of any other multiple of this guy. So if you put -1 to -1, so multiply by -1, or you can multiply by 2. As long as we don't multiply by 0, we're good. So those two spans, so 2 subspaces, are going to be the same. There are too many, and that's why we want to fix one of the variables to be 1. If there's more variables, then we're going to fix them as 1 and 0, and then 0 and 1. If there are 2, that means there's going to be 2 vectors. If there's 3, then there's going to be 3 vectors, and so forth. So this is the null space. Now, the null space is going to allow us to solve equations where this is not necessarily 0. So our goal is eventually to be able to solve all of these equations where this is not necessarily 0. Yeah. So in this example 1, we'll have a space, this space, the span of this, which is the solutions to all of these equations. We should review why we have a subspace. So one question we should ask is, why are all solutions to AX equals 0 a subspace? By the way, by X, we mean the vector. Yeah, a subspace of R m by n, so n, question mark. This is a little bit of a review of subspaces, and we cannot have enough review of subspaces. So a subspace, in a subspace, we have to have two things, 2 requirements. So requirements of a subspace. Well, 3 really. Can't be empty. So we have to have at least one element. Now, 0 always works. When you multiply a matrix times a vector 0, you get 0. So that typically, in this kind of equation, that always works. That usually checks. A 0 works. Yeah, no matter what, how bad the A is, there's at least the solution. As long as the size is correct, and they will be the correct size, yeah, we'll always get that. What is not always true in general is that if 2 solutions, if X and Y belong to the set, then so does X plus Y. So if X, Y, I hate to, so requirements of a subspace, let's call it V, yeah, or W rather, W. So if X and Y belong to W, then X plus Y also belongs to W. So we have to have closure under addition for a subspace to be, or for a subset to be a subset, a subspace rather. And if X is in W, then CX rather, CX is in W. And that is for any real number C. So if we multiply by a constant, we get still a vector in the subspace, and if we add them together, we get something. So we have to make sure that all the solutions to this equation are actually a subset, a subspace rather, of Rn. And this is in general. This is not just for the example one we were working on, but in general. That is always true. So a very, very informal proof. Okay, so first of all, A times the zero vector equals 0. And by that, I mean another zero vector. And those two zeros don't have to be of the same dimension. This could be a three-dimensional, this could be two-dimensional, whatever. But multiplying by 0 gives us 0 regardless. So let's assume, so I'm being very informal right now. So let's assume we're talking about W. And W would be the set of all the solutions to that equation. So W is non-empty, because 0 is one solution. So we have at least one solution. Now, if AX equals 0 and AY equals 0, then A times the quantity X plus Y, we have the distributive property of matrices, is AX plus AY. But we are assuming that's the if portion of this. We're assuming that each one of those products is equal to 0. So this is 0 plus 0. So we end up with 0. So that checks. It checks that if two elements belong to W, then their sum also belongs to W. How do we know something belongs to W? Because if A times that thing is 0, that means that thing belongs to W. That is the way we're characterizing W at this point. And then finally, if A X is equal to 0, I put parentheses because I was going to put something else, but the parenthesis is not relevant. Then, all right, so A CX, that's what I was going to put up here, and that's why I put parentheses. Now, C is a constant. If we have a constant across matrices, the constants may factor out, may be placed anywhere. So that is AX, but AX is the vector 0. And then we still multiply by C, but any constant times the vector 0 is still going to give us the vector 0. So that checks. So a constant times a solution is still a solution. Two solutions added together are together as one A solution, and there is at least one solution. So because of those three requirements are met, and this is very informal, then we have that this set of all the solutions to this equation is a subspace. Yeah, we had to talk about that. There's another space. There's three spaces that are relevant. Remember on my first page here, one of them is that the space generated by this row and this row, by doing row operations, we simplify that down to this row and this row. Wow, this is, yeah, this row and this row. So the space generated by the original two rows, 1, 3, 5, 2, 4, 6, is the same as the space generated by those two rows. And those two are simpler to work on. Yeah. Yeah, that is interesting. Yeah, so as a note of example 1, space generated by 1, 3, 5. Let's put them as vectors 1, 3, 5, and 2, 4, 6 is the same as the space, because we're talking about space, generated by 1, I'm looking 1, 0, negative 1, and 0, 1, 2, which is a lot simpler to understand. Another way to say this is that the span of 1, 3, 5 and 2, 4, 6 is the same as the span of 1, 0, negative 1, comma, there should be a comma here, and then 0, 1, 2. And those are way simpler because then we can see the interaction between um, the two vectors. The column vectors, the generation of column vectors is a little more tricky. Informally, let me talk about dimension before I continue, because the dimension is what is kind of important here. So informally, and actually semi-formally, informally, so dimension is the number of fewest generators of a space. So the space, the null space is generated by those two, and we cannot simplify them anymore. Once we have a row reduced echelon form of a matrix, we cannot really simplify it anymore. And once we have that, that's why it is valuable to change from matrix into a row reduced echelon matrix. Then we have the bare bones. Any redundancy is going to be gone. Boy, there's a lot of things going on in this video. Yeah. So again, the dimension is the fewest number of generators, the number of fewest number of generators of a space. That's the dimension. So the dimension of this space is 2. That is going to be relevant. So the null space has dimension 2 in this case. So we are still in example 1. Dimension of null space is 2 because we need 2 generators. Well, those 2 generators. Wait a minute. I misspoke here. I was confusing one thing with another. And just the last sentence. That's not the null space. That is the space generated by the row, which is a different space. It is still going to be relevant, though. That's not 2. The null space was on the previous page here, and the previous couple pages. There it is. The null space is generated by this vector, 1, negative 2, 1. So that is the null space. Yeah. So in this, and there is only one vector. So what is the dimension of the null space? 1. So dimension of null space is 1. I was confusing that with the span of the row vectors. But there's a relationship because that is 2 and that is 1. So this is dimension 2 and this is dimension 1. And it always is the case that the dimension of the null space and the dimension of the span of the rows adds up to the total number of columns. So dimension of space generated by rows plus, and there's many different ways to write this, dimension of space generated by rows, which is in that example 2, plus dimension of null space is equal to number of columns. Yep. By the way, this is also called the rank of A. Rank of A, which is the same thing as the number of pivots. This is the same thing as the number of free variables or free columns, which makes sense because a free column doesn't have a pivot. So those two add up to, so when you have all the columns, there's only two things that can happen. A column has a pivot or doesn't have a pivot. So when we put them together, you get all of them. Yep. And all of that has consequences as far as dimensions go. Dimensions of subspaces that are related to a matrix A. Yeah. The only one that I think is tricky is the dimension of the columns. No, not the dimension, but the actual space generated by the columns. The dimensions are preserved, but the subspaces generated by the columns can be a little tricky. I don't think we're going to focus too much necessarily. Practice this. I don't think any of this is simple. I think we have to get used to a lot of the mechanics of the matrices. Let's do a couple examples of the null spaces. Okay, let's say you have, oh, I was looking for an example number because I want to keep track of the numbers of the examples. You may say, well, last example was 1. Actually, last example was 4. What happens is that we went back to 1. So let's do example 5. Let's look at a matrix 1, 2, 3, 1, 2, 4, and then 0, 1, 2. And we want to find the null space of this matrix. Yeah. So can we find it as is? Perhaps, but it is rather complicated because there's too many things going on. An x plus 2 y's plus 3 z's. Now here we got a 3 by 3, so we do have a 3 by 1. So this vector is correct. This dimension of the vector is correct. Anyway, so we have x plus 2 y's plus 3 z's, and we got a bunch of different things going on here at the same time. We want to sort this out by changing this into a row reduced echelon form, which has ones in the pivots, and then we have zeros above the pivots and below the pivots. So right now we have a 0 here. It's easy to convert this second row into, well, this element here into a 0 by subtracting from the first row. So instead of writing the whole equation, I'm just going to go ahead and work this matrix through 2, 4, 0, 1, 2. So we're going to transform this by taking the second row and taking away the first row from the second row. So the first row is going to remain as is, 1, 2, 3. 1 minus 1, 0, 2 minus 2, 0, 4 minus 3. 4 minus 3 is 1. And I paused for a moment because 2. So x, y, z, x, y, z, x. So changing the rows, because we want this guy, we want a row echelon form, which means we want to go down diagonally, 1 zeros. And then we want to have 0, 1, 0. And if possible, 0, 0, 1. But the reason why I was thinking, pausing for a moment, is because x, y, z, x, y, z, and still x, y, z. So exchanging the rows is not going to change the order of the variables. We're still going to have x, y, z. So we're going to exchange row 1, rather row 2, and we're just going to exchange with row 3. Row 2 and row 3 are going to be exchanged. So we're going to have a new matrix, 1, 2, 3, 0, 1, 2, 0, 0, 1. Oh yeah, we're going to be able to do this. So subtract from the first row the second row. So row 1 minus row 2. Okay, so row 1 minus row 2, 1 minus 0, 1, 2 minus 1. Oh, I do want to end up with a 0, so we need to subtract 2 of those. 2 minus 2, 0. 3 minus 4, negative 1. Okay, and then we have 0, 1, 2, 0, 0, 1. I'm going to copy this on the next page to keep it together, even though I could probably just do the change, but no, I just want to copy it down. 0, 1, 2, 0, 0, 1. And now we want to wipe off those 2 elements on that third column. So we can add row 1 plus row 3, and that creates that causes that to be 0. And the first 2 elements are not going to be changed because we got 0. So we are going to add this onto that, and we're going to take away 2 of those from this one. So row 2 minus 2 times row 3, and we're going to end up with, okay, so 1, O. Adding those together, we're going to end up with O, O1, 2 minus 2, O, and then we leave this alone. Okay, so the original problem, 1, 2, 3, okay, so 1, 2, 3, 1, 2, 4, 0, 1, 2, x, y, z equals 0, 0, 0, which is a system of equations of 3 unknowns and 3 unknowns with 3 variables. Remember, that is x plus 2y plus 3z equals 0, 1x plus 2y plus 4z equals 0, and y plus 2z is equals 0 is equivalent to 1, 0, 0, 0, 1, 0, 0, 0, 1 times x, y, z, because we did row operations without multiplying by 0 or dividing by 0. That is very important, which means we are just eliminating variables without actually changing the nature of the solutions. So what this means is that x has to be 0. So there's only one solution. So, well, x has to be 0. There's no other option. X equals 0. Y has to be 0. And z has to be 0. There's only one solution. There's a 0-dimensional space. Even though it has one generator, by the way, the number of generators has to be, when we are talking about dimension, the generators cannot include 0. But if it is 0, then if there's only one generator, which is this guy, 0, then um, the dimension is 0. Yeah, let me make a note of this. If, whoops, if um, the only generator of a space, whether it's subspace or not, is 0, the vector 0, then um, the dimension of the space is not 1, rather 0. Yeah, because before in this video, I said that this fewest number of generators of a space or subspace is the dimension, except if the generator, the only generator is 0 itself. Then that is not the case. Uh, because one may think, oh, so the dimension is 1. No, no, no. If we start out with dimension with the vector 0, and that is the only generator, then the dimension is 0. Yeah. 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 So there's only one solution, 0. No more solutions. We have a what is called a trivial space. Um, yeah, just one solution, and that's it. There's no more solutions whatsoever, just one point, as opposed to a line, a plane, a space. Yeah. So how do we get, that was example 5, isn't it? Yeah, 5. Example 6. If you have 1, 2, 3, 1, 2, 3, let's keep the other one simple, 0, 0, 1. So let's say you have this matrix instead, and we want to solve for x, y, z equal to 0, 0, 0. Well, a simple reduction here will cause this to be, how can we simplify this? Well, just subtract, the second row from the first row, and we end up with, if we subtract the 2, we end up with zeros here, and then we can change those two. And so there's a couple things we're going to do. We can get a row of zeros, exchange those two. So now we got the row of zeros on the bottom, 0, 0, 1 on the middle. But then we can take away 3 down, or we can take 3 down by subtracting 3 of these ones from the first, and we end up with 1, 2. So this is equivalent. I'm not showing blow by blow the steps, but you can go through them. 1, 2, 0, because this one will knock down that 3. All of those elements are going to be reduced, and we can put 0, 0, 1, 0, 0, 0. X, Y, Z equals 0, 0, 0. Okay, so this says y has to be 0. And that's a pivot point, by the way, a pivot element. This is a pivot element. So how many free elements do we have? 1, which means that the dimension of the null space is going to be 1. Let's come up with a generator of the null space. Oftentimes we're going to be asking in what we are studying right now for the null spaces. So what generates a null space? So we want to figure that out. So the free variable is going to be the y variable, because that corresponds to the second column. If we set y to be 1, that will cause, yeah, so perhaps we should write down the equation. So x plus 2y, that's what this row is saying. X plus 2y is going to be 0, which means x is opposite of 2y. So if y is 1, x is negative 2. All right. Z automatically is So when we multiply z, so no x plus no y plus a single z is going to give us 0. So z is 0 no matter what. There's no out of that. And this isn't telling us anything because 0x plus 0y plus 0z is 0. Well, that's not giving us additional information. So actually, z could be anything. Oh, that's interesting. Can z be anything? Huh. So one generator of the null space. So we want to find the null space. Well, before I do that, let me double check something. So 1, 2, 0, 0, 0, 1, 0, 0, 0, multiplied with 0, 0, 1. Does that give us 0? 0? No, that doesn't give us 0. So z cannot just be anything and give us 0 because I just proved it here. This is going to give us 0, 1, 0, which is not 0, 0, 0. So what can I say about 0? Oh, I'm sorry. Z has to be 0. It's right up here. In order for this equation to work, z has to be 0. Boy, that was a little confusing. Okay. And so the free variable is y. Whatever y is, then x has to follow suit. It has to do this. Yeah, so the solution will be, for instance, if y is 1, x has to be -2, and this is got to be 0 regardless. So the span of this guy is equal to the null space of the matrix 1, 2, 3, 1, 2, 3, 0, 1. There we go. So the dimension of the null space is 1. The rank is the number of pivots. That's 2. And that means that the space generated by the rows has dimension 2. And that is reasonably clear in this example because this row is equal to that row. So one of those two rows is unnecessary. One of those two rows is redundant. So we only need 2. And that makes this reduction to row echelon form makes that more clear. All we need is this guy and that guy to generate all the rows. The dimension of the space generated by the columns is also 2. But I'm not claiming that the space generated by this column and by this column is the same as the space generated by those 3 columns. And I can clearly tell you why. Here, the space generated by those 2 columns doesn't have a z value other than 0. But here we could have a z value that is not 0. So we have to be careful. The dimensions of the columns is the same, but it's not generated by the same column vectors. On the other hand, the row vectors, if you substitute those three vectors with those 2, the spaces generated by those 3 vectors and those 2 vectors are going to be the same. That is not completely clear at the beginning. And let me finish up with one more example. Let's pretend we have 1, 2, 3 as a column, 1, 2, 3, and then 0, 0, 1. So I'm doing the transpose of example 6. Example 7 is a transpose of example 6. So remember, one of the things we're going to be asking is for the null space, x, y, z equals 0, 0, 0. Whoops. If we subtract this two of those minus that, we end up with a row of zeros. We can flip, and then we can, well, before flipping, we can take three of those from this, and we end up with 0, 0, 1. So this is equivalent, this system of equations is equivalent to 1, 1, 0, 0, 0, 1, 0, 0, 0. Again, this row minus twice that row gives us a row of zeros, which can go on the bottom. This row minus 3 times that row gives us 0, 0, 1. There it is. And that's as simple as we can get. So the null space, so how many free variables do we have? 1. Yeah. So the null space, x, y, z equals 0, 0, 0. The null space will have x plus y equal to 0. Again, z is equal to 0, but I'm not going to fall for this. That doesn't mean that z is free. Y is the free one, because from here, we can get that x is negative y. So whatever y is, x has to follow. If y is 1, which we want it to be 1 to get a special solution, then x has to be negative 1. If y is 1, x has to be negative 1 because of that negative. So one special solution is 1 for y, because that is the free variable. Z is not a free variable because z has to be 0. It cannot be free. That's kind of a little confusing. And x has to follow whatever this equation says. So this is a special solution. And that is, all the solutions have to be a multiple of this guy. They cannot be anything else but that one, the solution to this original equation. Yeah. The rank is 2 because we got 2 pivots. The dimension of the null space is 1. And the rank plus the dimension of the null space, or the number of special solutions, is equal to the number of columns. Yep. Please do a lot of problems and examples. After doing a few of them, you get the hang of, oh, okay, I know what the rank, null space is, and the rows and the columns. You get a hang of it. But we really want to do a few examples to understand this better. All right, we're going to stop the video here.